Okay, so we'll start again. Our next speaker is Harini Desiraju from the University of Sydney, and she will tell us about the solutions of Painlevé equations and Fredholm determinants, a Riemann-Hilbert approach.
Thank you. Okay, am I audible? There is a weird reverb. Okay. This talk will be slightly technical, but the idea is to introduce some techniques to build some Fredholm determinants for any kind of integrable systems. My example of choice will be Painlevé II, but all the things that I'm presenting today are equally applicable for all kinds of integrable systems. Honestly, if you have a Riemann-Hilbert approach, then you can try to apply them. I can't promise that it will always work, but I can tell you when it works and when we need newer techniques. Okay, so the plan of the talk is the following. I will start with introducing what is the notion of a tau function for integrable systems and Painlevé equations. Then I'll talk about the general solutions of Painlevé II, by which I mean the two-parameter family of solutions. And I'll show you how you can express them in terms of some Fredholm determinants. And I'll conclude with some open questions and some other examples that I can apply these kind of techniques or analogous techniques to. Okay, so Painlevé equations are a class of second-order differential equations, ordinary differential equations, which have a very interesting property, is that you can start from Painlevé VI, which is an equation with 4 parameters, start making conditions on the parameters, and get all the other Painlevé equations. So in some sense, you can go from Painlevé VI equation all the way to Painlevé I. And this goes under the name of Collison's diagram. A similar diagram exists for known special functions, starting from Gauss hypergeometric functions all the way to Airy. Now, there are 2 important points I want to note at this point, at this stage. One is that people who are familiar with Painlevé equations will notice that the special solutions of Painlevé are usually given in terms of some sort of a special functions. So, for example, there is a solution of Painlevé II that starts from Airy functions, and you can produce a lattice in some sense. The second important point is that these equations are integrable, which means that associated to these integrable systems, there is some sort of a monodromy representation, through which I can construct a Riemann-Hilbert problem. This is just a synopsis of what I'm trying to say. All the words will be expanded in full detail once I start the Painlevé II equation. Now, what happens is that when you write a Riemann-Hilbert problem of these Painlevé equations, you can express some sort of a local parameter C. So locally, you can describe the solutions of these Riemann-Hilbert problems in terms of some form of special solutions. And this is the main property I'll be using full-fledgedly in the techniques I'll be presenting today. So this is the singularity structure of Painlevé equations. So because they're integrable, you can write them in terms of some linear equations which have some singularity structure. And like, as I mentioned, when you have the differential equations, you have this diagram, you have a similar diagram, but from a geometrical point of view or from the singularity point of view. You can think of Painlevé VI as studying some isomonodromic deformations on a sphere with 4 simple poles. And the Collison's simply means that you, well, not simply, it's a hard procedure, but it is equivalent to collapsing the poles. So you collapse these 2 poles, for example, you get Painlevé V, which has 1 irregular singularity and 2 simple poles. Ignore the red bands for a bit, because that will make sense towards the end. And similarly, you can obtain all the Painlevé equations. Now, I like to think about this diagram as 2 different families of equations. There is the top layer, the ones with red bands, and then the bottom layer, the ones without red bands. And the reason for it, I don't think I'll mention, but this is a fascinating property, that the top layer and bottom layer share quite a lot of common properties, which means that usually if you solve one problem in the top layer, you will then have, you can apply these kind of techniques to all the other equations in the top layer. And bottom layer is its own story. And today I'll be focusing on this case. Okay. So the result I'll be showing is the following. You have the Painlevé II equation, which is a second order differential equation. Sometimes you find an alpha here. Maybe I'll write it down. Sometimes you find this alpha here, but today I'm setting it to 0. So I'm thinking about, this is called a homogeneous Painlevé II. And I'll also briefly touch on what happens when you activate the alpha. So what I'm going to show you today is that this solution, which is described by this tau function, how I'll come to it in a minute. Oh, also this x and t are related. I'm so sorry. I think. There is a slide inside. So they're described by this Fredholm determinant, which is here, plus some regular terms. I will not show you the full details of this f. This is like a 2-page long thing, but it is explicit. It is explicit in terms of some special functions. The thing to note is that since it's a second order differential equation, you should have 2 parameters, and those are the Stokes data. And t is the time. Okay. So, also I want to mention that the asymptotics of the Painlevé II equation pop right out of the determinant. Since we are talking about all orders, all the subleading orders can be studied through the determinant, and the asymptotics really just pop out. And this is quite a powerful formulation for this reason. Okay, so let me start with motivating the Lax matrices of Painlevé II. This equation, which is a second order scalar equation, can be written as a set of 2 differential equations that are linear but matrix valued. Sigma 1, sigma 2, sigma 3 are the Pauli matrices. And the consistency condition of the Lax pair, which just means that dx and d lambda are commutative, gives rise to this equation. Actually, this will give you some sort of an anti-diagonal matrix that has 2 equations. One will be v is u prime, and v prime is 2u cubed plus xu. Alpha I'm setting to 0. So these are the equations that you get from the Lax pair. The important point comes from this lambda squared term. So how do you understand the singularity of this equation? So you want to understand where the singularity is of this y, the solution y. Lambda squared here indicates that there is a third order pole at infinity, because this is the logarithmic derivative, so I'll show you what happens here. And the Riemann-Hilbert contour, because it's lambda cubed, maybe I can go a bit further to make it easier, the exponent of the solution will be 4/3 lambda cubed. And this lambda cubed induces 6 Stokes rays. So this is easy. You can just write it on Mathematica. You get all these rays. So the Riemann-Hilbert problem for this solution, so this solution is actually multi-valued because of this theta. So you can define a single valued function, which is psi, which is just y times exponential of this term, well, which is here. And you can define it in the following way. Psi is piecewise continuous, so it is defined in each of the Stokes sectors. And plus and minus are given with this convention. Plus is here, minus is here. So for a ray, for a ray here, for any Stokes ray, this is the positive side and this is the negative side. So when you go here, this will be the positive side and negative side, and so on. So this is how you define the Riemann-Hilbert problem with the usual prescription of positive and negative. There are 6 rays, but not all the jumps on these 6 rays are independent. So you can see that everything depends on 3 parameters, S1, S2, and S3. Okay, so out of the 6 parameters, 3 of them are dependent, and the remaining 3 satisfy a constraint. So all in all, you have 2 independent parameters, which is consistent with the fact that I have a second order differential equation, and I'm studying the 2 parameter solution family. Okay, so we have a constraint, you have 2 parameters, and the asymptotic behavior is such that psi goes to identity. And there is this exponent that plays a very important role. Now for the tau function. In the theory of integrable systems, a very important notion is played by tau functions. And the story starts like this. Now, it must be a bit overwhelming to see 3 definitions, but these are all the same, and I'll go into the details in a minute. So you start with the Riemann-Hilbert problem, and for any such problem, you can define a Malgrange one form. The terminology of one form can be ignored for the purposes of this talk, but it is still an important notion. It tells you when you have a wrong equation, you can immediately check and see what you have. So that's the analytic purpose of this one form. So you can define such a quantity that is the integral depending on the jump and the negative part of the solution, which is coming from here. Now, the tau function is described as a logarithmic potential of this quantity. It then turns out that the solution is given by one more derivative of the tau function. Now, there is a reason why we want to study the tau function instead of the solution. There is also something called the sigma form of Painlevé equations, for which the tau function is the solution. And the second thing is that tau function appears in way more applications than the solution itself. A very notable example is of the airy kernel. The airy kernel is a tau function, not the solution. So wherever you see the applications, the key role is really played by the tau function. And it so happens that if you want a nice formulation, an integral representation of this tau function, then the closest you can get is a logarithmic derivative of it. So my objective now is to show that this can be written as a Fredholm determinant using this formulation. So starting from the logarithmic derivative, I want to pull out all the information about the tau function. So tau function is also some sort of a litmus test sometimes in the following sense. The zeros of the tau function exactly are the places where the Riemann-Hilbert problem is not solvable. So Riemann-Hilbert problem in this sense is a map between the initial conditions so let me call this x0 really, and S1, S2, S3 plus constraint or modulo constraint. This map is not invertible where you have zeros of the tau function. So it picks out exactly the points of this map. It also happens that when this is 0, those are the poles of the solution. So when you saw all the tree-trunc solutions and so on, what I'm thinking about is really zeros of the tau function. And since zeros are analytically easier to study than poles, that's one more reason to think about things in terms of tau functions and not the solutions. Okay, so what is already known about these tau functions for Painlevé II? There is a family of solutions called the Ablovitz-Segor, which are just given in terms of airy functions. And the equivalence between this special family of solutions and the Stokes data is just by setting one of the Stokes parameters to 0. So if you want special solutions on the initial condition side, you just put a special constraint on the monodromy side. Okay, so these solutions are described very nicely in terms of the very famous airy kernel. Airy kernel has the following form. And this is called the IIKS. This has the form of an IIKS kernel. And I'll define this kernel in a minute. And it will also play a very prominent role in the rest of the story. OK, so any kernel is an IIKS kernel or an integrable kernel that has the following form. And this is in itself a tau function. There is also a slight side note, which is that you can write this in terms of Toeplitz operators on a real axis, and that was shown by me in this paper. OK, now on to the general solutions. Now I'll start from the Riemann-Hilbert problem and show you how to construct kernels of this form, but for 2-parameter solutions. So there is a 4-step strategy, and it all really depends on, yeah. Oh, the support of this kernel is on a line that starts from S. This is the time, basically, to infinity. No. This is just a support of the kernel. So the basis is defined on a half interval. More questions? OK, so there is a 4-step process of understanding how to construct these determinants. The first step is to transform parabolic cylinder, transforming the Painlevé II Riemann-Hilbert problem into parabolic cylinders. And I want to remind you that, OK, I can't reach that. Oh, I guess you can't see it. OK. So I started from this Riemann-Hilbert problem. Oh, OK. So I'm starting from a Riemann-Hilbert problem on 6 rays. So now I need to make it more manageable. If anyone is familiar with the nonlinear steepest descent, it's like peeling the layers of the onion. You're trying to understand what is the basic quantity that you can completely determine analytically. So step number 1 is to understand where parabolic cylinders are hiding inside this Riemann-Hilbert problem. Second one is the key technique, in my opinion, which is that you take the ratio of the global solution and local solution and transform whatever you have here into a simpler contour. So after different degenerations, I get to a simple contour, which is just the imaginary axis. And I'll then define a Fredholm determinant corresponding to this imaginary axis. And then it's like putting back the pieces of the Russian doll. You're just constructing, you're tracing everything back to what is happening on the full contour. OK. Step number 1, which is transforming this Riemann-Hilbert problem. OK. I make a change of coordinates. I hope I got it right. Yes, I did. You make a change of coordinates, which are slightly non-trivial at the first sight, but these are supposed to, these coordinates will change this Riemann-Hilbert problem not only, but whatever you get in the end is more, not prone, but you can do the asymptotics, you can read off the asymptotics at minus infinity because of this transformation, because you're going to minus x. OK, now under this transformation, the characteristic exponent, which I promised I'll write down and then I forgot. This was lambda cubed, 4 lambda cubed over 3 plus minus. This was the original exponent. Now under this transformation, the time part comes out. The time part comes out, and theta z, in terms of z, is just a cubic. This cubic has 2 stationary points at plus and minus half. So this transformation will first induce 2 stationary points at plus half and minus half. Then I'm also defining this quantity nu, which is defined in terms of S1 and S3, you can just keep track of mu. Okay, everything is normalized at infinity. Now this very nice graph now transforms into this, which I'll write down for future purposes. So what is happening? All the S1, so this was S1, S2, S3, S4, S5, S6. The corners are fine. S1, S6, S4, and S3 are preserved in this picture. The transformation is really happening at the level of S2 and S5. So that is giving us 4 extra rays and a diagonal jump, whereas D is diagonal. Okay, and these points are exactly plus and minus half. So the takeaway is that when you try to make a transformation, it usually induces some extra stationary points, and around that points, you get a simplified contour. The main thing is that now, around exactly these points, you have a transformation that lets you study the local solutions, which means a solution in the vicinity of the stationary point, completely in terms of parabolic cylinder functions. So the way it happens is that you make a conformal map. So this is the map that is angle preserving. And this map, what it is doing is that it's rotating the whole thing. So a good way to track of where the rotation is happening is keeping track of the diagonal jump. So the diagonal jump is here, and the diagonal jump is here. So it is rotating everything such that the diagonal jump is exactly mapping the parabolic cylinder function. What this means is that there is a map from the piecewise functions that are completely defined in terms of parabolic cylinder functions to the piecewise functions inside here. So that is given by this one. Now it looks a bit daunting, but the main thing to understand is that there is a nu. D nu is the parabolic cylinder, and Z0 is given by some Wronskian of the parabolic cylinder. Starting from Z0, using these conditions, the jump functions, you can then compute what each of these piecewise function is. So everything is in terms of parabolic cylinders times some constant matrices. One more thing is that the parameters, the Stokes parameters that are in this diagram are all determined by mu. So we are preserving all the information that we got from Painlevé II. Okay, so if I just want to study everything in the vicinity of, I also have a red chalk here, if I call this phi r, it is determined by parabolic cylinder functions times some other factors that are explicit. So the main thing here is that I'm able to study the local parametrices in full explicit detail. Although it is lengthy, it is still explicit, which means that we can do numerics on it, for example. Moreover, there is a symmetry between what is happening on the right side and on the left side, which is here. And this symmetry lets us also compute what phi L will be in terms of phi r. So now, what did I do? I went from this to this with both the right and left parametrices completely described in terms of parabolic cylinder functions. Now, the problem reduces to, can I define a better Riemann-Hilbert problem with these local solutions? Can I do something better? Because at this point, this isn't too manageable for me. Okay. Now comes the main trick. So I'll write it here. Key technique. Ratio of local and global solutions implies simpler Riemann-Hilbert problem. Now, this technique transcends the notion of Riemann-Hilbert problems, really, and can be used for several amount of applications. Okay, so what I'm going to do now, take the ratio of the local and global solutions. Global solution is psi, that was on this whole contour. Take the local, take the ratio with the local solution, phi r0, which is here. So phi r0 is here. And phi L4 will be here. Now you can ask me, why are you not taking complete phi r? You can, but everything else cancels out. And because we are aiming for the imaginary axis, the only relevant parts will be the solutions that actually touch the imaginary axis. So ratio of the global solution with the local solution touching the imaginary axis. This will do the following. It will cancel out all the jumps, and it will induce a new jump, but on the imaginary axis. So if you plug this back in, then everything cancels out because you're taking the ratio, and you have a rather simple looking function with just a single jump on the imaginary axis. But, okay, so this is what's happening on the imaginary axis. The only, oh, sorry, this was here. This was here, and that was also here. Okay. So we are only concerned about what is touching the imaginary axis. But then we paid a price for this, which is that while doing this transformation, we induced a second stationary point on -1 and +1. Oh, sorry, -1 and +1. Which means that we only have limited capacity of really studying this jump. We can't analytically invert it everywhere on the complex plane. So we are really bounded near the vicinity of the imaginary axis. Okay, now how do I construct a Fredholm determinant for this imaginary axis? I use the theorem of IIKS, which is Izergin, Koropin, and Slavnov. These kernels really started by understanding quantum correlation functions of Painlevé 5 and 3, but now this has become a toolbox where, given a Riemann-Hilbert problem, with appropriate factorization of the jump, you really can construct a Fredholm determinant such that this determinant, this kernel, 1 minus k, is invertible only if this Riemann-Hilbert problem, with a very specific factorization of the jump, is solvable. Which means that the determinant of this kernel plays the role of the tau function, because we are understanding tau function as points where its zeros determine the solvability of a Riemann-Hilbert problem. So the jump needs to take this form of f and z such that f transpose z is 0. This is a constraint that will be very important in the next part. So now the idea is, okay, I have a jump on IR, which is given in terms of L4 and R0, which are all parabolic cylinders. Can I write this in this form? So now my problem has simplified from write the tau function for this very big problem to factorize this jump in a nice way. Okay. The jump has the following form. I'm just showing you because I want to make sure that I'm not lying. Everything is in terms of parabolic cylinders. This psi and chi are both just transformations. So psi is a transformation. I'm sorry, this is zeta. Okay, my Greek isn't great. But this is a transformation that took this to parabolic cylinders. So let's call this left and right, yeah. So everything else is a coordinate, everything is explicit, and H depends on nu. Okay. I can decompose any SL2 matrix as lower, upper, lower triangular, diagonal, and upper triangular matrices, which means that I can transform this Riemann-Hilbert problem again into a set of 3 contours with jumps which are lower, diagonal, and upper triangular. But this will not help me with the factorization because of the diagonal jump. When you have a diagonal jump, the goal now is to write the jump as 1 minus 2 pi I f z g transpose z such that f transpose z g of z is 0. And this constraint is not solved for diagonal jumps, which means I have a problem yet again. But when you have a diagonal jump, you can solve it explicitly. It has an explicit local solution, just in terms of its exponential. So I use my trick again, ratio of local solutions and global solutions. So you solve the diagonal, and then you take the ratio yet again. So this transforms the 3 contours into 2 contours, which are lower and upper. Lower triangular and upper triangular. I don't think this is visible, really. Is this better? Maybe. OK. OK, so I started from here. I came all the way here. Now, because you only have lower and upper triangular matrices, you can write your jump in the desired form. So you sorry, how much time do I have left? Oh, 18 minutes. Oh, I have plenty of time. OK. Sorry, I got phased off. OK, so I'm starting from this particular triangulation. You have lower and upper and a diagonal matrix. Diagonal matrix can be explicitly solved in terms of this var phi. And this usually takes the form, I'm out of space. Phi is exponential log a z or w, w minus z dw 2 pi I. This is a singular equation. This is the solution of the singular equation you get from a diagonal jump. So considering this as the local solution, oh, I shouldn't have used y here, but OK. So if I again use my trick of local versus global solutions with this diagonal jump, I get to a Riemann-Hilbert problem with jumps only on a set of 2 contours. Now I can write jump as I like it. It'll be messy, but I can still write it. Now, chi1 and chi2 are characteristic functions, which means that they're 1 on the contour and 0 everywhere else. So they are the functions that let you choose the contour you're on. OK, so f and z are vectors. And you can write your final jump that is on set of 2 contours in the desired form. And because they're only lower and upper triangular, it satisfies the constraint we want it to satisfy, which means you can write a kernel. You can write a kernel with f of z and g of w that needs to be paid attention to, which is a 2 by 2 kernel, but on a set of 2 contours. Now I can do better in principle, which is that after some laborious computations, I can reduce the kernel, which is on set of 2 contours, which is not really nice to do analysis, onto simply 1 contour, which is on IR. But the details are a bit too murky, so I decided to skip it. But now I have time, so maybe I'll show you. But everything is explicit in terms of parabolic cylinders, and you have a very nice kernel that sits on the set of these 2 contours. Maybe I'll write L tilde and U tilde. OK, now what? Now comes the problem of saying, OK, great, I have defined a kernel here. I got a determinant here. But what about the tau function there? This is what I wanted to know. And this is when I use the integral formula that I showed you in the very beginning, which was it's an integral over whatever contour you're considering, which means that if I'm considering this contour, this can be replaced by L tilde union U tilde. So depending on whichever contour you're using, sigma trace inverse minus prime or dz dt jump inverse dz over 2y. In other words, all I'm trying to say is that if you take the logarithmic derivative of this determinant, then you can try to, by these transformations that you did for the Riemann-Hilbert problem, you can try to recover the tau function for the full Painlevé II. This blank slide was intended to show what I do on the board. Okay, so now comes the Russian doll step, where you gather all the blocks that you had and you want the big one. Okay, now the little one is sitting here, which is the determinant on just these two contours. Is this visible? Okay, I'll just show it just in case someone doesn't see it. I'm here. Well, it's a bit of a mess, I'm sorry. I can take a picture and send it in the end. Okay, I'm here, and then I take the logarithmic derivative here and try to recover all the steps, because all the Riemann-Hilbert problems I'm showing are connected through some very definitive transformations. So this is the result you get, but I don't want you to focus on all the black stuff. All the black stuff is all explicit in terms of parabolic cylinders. It's really complicated, but it is explicit. I can put it on Mathematica, and Mathematica goes crazy because it doesn't know how to do this transformation. You need to be very, very careful. So after you really toyed around with Mathematica after 2 months, you will get some numerical results about this statement. Okay, so here sits my determinant. You backtrace it. You get to the determinant on LDU, which is here. So in the second step, I'm in the three contour phase. You go back. Now you're with just the imaginary axis, which is an IR, and then to tau of Painlevé II. So in other words, the tau function of Painlevé II, the logarithmic derivative, is related to the tau function through a very straightforward yet complicated series of steps. Everything you see here, again, is really explicit. I wish I can show you what this looks like. It took 2 pages. Anyway, so you can do everything explicitly. But what is the punchline? What is the punchline in the slide is the following. If I want to know where the zeros of the tau function of the Painlevé II tau function are, you don't need to worry about all this, because these are all regular terms. So analytically, they're well defined. They don't have poles. They don't have zeros. So all the zeros of the tau function are really coming through this determinant. So this is really like the pith of the tau function. So everything is in this determinant, and this determinant also, through these series of transformations I made, determines when this Riemann-Hilbert problem is not solvable, because that's really the only relevant part in some sense. And this very nice thing here is the asymptote of the Painlevé II tau function for t going to minus infinity. Okay, so I hope I convinced you that there are techniques available to construct determinants. Now I want to go to conclusions and show you the first picture I showed you, which is this. Now when I tell you that when you want to study the tau functions of the upper half, all you do again is look at the local solutions, which in this case are hypergeometric functions. Use my trick, which is now gone. Well, okay, it's not my trick. I should stop calling it my trick. People have done it before, but I just want to put it in context of this particular talk. Oh. Okay, so for the top layer, you again use this trick, which is take the ratio of local and global solutions. Here the local solutions are hypergeometric, similar to how here I had parabolic cylinder, and you will get a Riemann-Hilbert problem not on the imaginary axis, but on a unit circle. And then you have a different number of techniques using Toeplitz operators, using many other techniques, many other Fredholm determinant techniques on the unit circle to write the determinants for the top half. And again, you can still read out the asymptotics, and all the subleading order of the asymptotics lie in the determinant. You can also do a minor expansion, which means that you can write a series representation of these Fredholm determinants, which is also quite nice and has really nice ties to conformal field theories, for example. So yeah, this case is solved. Everything up is solved. Now I want to, I wanted to show what happens here, but I covered it in words. And this goes by, well, I named it CGL methodology, but this is given by Cafasso, Gavrilenko, and Lissovi. So they have a paper where they show a similar way to do Fredholm determinants, but on a unit circle using Toeplitz determinants. And the combination of Toeplitz determinants is called the Widom constant. Okay, so now the open questions. How can I extend the present formalism to study Painlevé I? And since we've been seeing quite a lot about Painlevé I, can I say something about the two-parameter family? First thing. Second thing is that there are also quite a lot of results coming from topological recursion and resurgence for Painlevé I. Can I make contact with their computations? And the second one, which is much more explainable in the present context, is what happens when you have Painlevé II, but once you generate alpha. Once you generate alpha, you have a monodromy at 0, which complicates my life because such a nice splitting of the local parametrices is no longer available for alpha not equal to 0. So this is where I think some new techniques are needed, but there is a good motivation to do that, because once we understand what is happening for alpha not equal to 0, we also can use the same methods for Painlevé IV. So if we solve that one problem, we can solve all of Painlevé equations. Not only, but also we can solve quite a lot of. So for example, MKDV is another example that I tried using this method. It's quite, the easy asymptotic is still easy. So there is a t going to infinity asymptotic, I believe, is still defined on the IR, and that I can write as a determinant. But there is another asymptote which is hard for MKDV, and that will also have a very similar structure. So there is just one step towards solving quite a lot of problems. So there is a good reason for me to think about it. The other is to extend these methods also to Q Painlevé equations, because such a splitting is also possible for Q discrete systems. I think I'll stop here.
Okay, thank you very much. Thank you. Are there questions and comments, please? Saleh, yes.
Yeah, I didn't quite understand parts of your talk. So this is probably more from ignorance. So I didn't quite follow. You had a log term, which you said was the important part.
Yeah.
And what was your conclusion about that? Are you able to say something about what the zeros are of the determinant?
Yeah. So the zeros of this determinant, they have to be computed numerically.
And then where does the condition at infinity, you pointed out the last term, it says something about.
Yeah.
This is related to the condition at infinity,
yeah.
Correct? But which particular, is there a particular solution you're picking here, or it could be anything?
Oh, here I'm considering purely imaginary solutions of Painlevé II. So for two-parameter family of solutions that are purely imaginary.
As x tends to minus infinity?
Yeah.
Okay.
For x tends to minus infinity, you can see that in the asymptotic limit, this drops out. It doesn't have a leading order behavior. So the leading order behavior is determined by this factor. But once you have a determinant of this form, it's 1 plus some small term.
And you mentioned with the alpha term, you have some difficulty because you don't have the you don't come back to the same thing when you go around, right?
Yeah. Yeah.
And you can't fix that with some explicit function with a branch single branch point or something like. You can't. It's not fixable.
Okay, so if I just want to study the Riemann-Hilbert problem and study the asymptotics, then I can do it for alpha. This is actually done by Novokshchanov. It's I think okay, it's done in their big book. But the problem when alpha is not 0 is that this kind of very nice splitting I had in terms of parabolic cylinders disappears. It becomes harder because I didn't have anything at the origin. The splitting was quite nice, and there was nothing really preventing me to define things on the imaginary axis. So once I turn it on, something non-trivial happens here. So that splitting is still.
So I was suggesting that whether or not if you can introduce some kind of a, so for instance, if you have a function which has a simple monodromy, like which you can fix it by pulling out a factor p to the whatever variable to the power gamma times a function which returns to itself. You can't do that in this case.
No.
I see.
At least not yet.
Thank you. Yeah, Alba.
Thank you very much for the very nice talk. I have a question. So sometimes if you fix the initial condition of Painlevé in a certain way, you also have, okay, even with the microphone, wow. So sometimes if you fix the initial condition in a certain way, there are also other type of Fredholm determinant solution, right? Like for example, in the Painlevé III, you have the type of Fredholm determinant that you presented, and then you have this other like McCoy and company type of Fredholm determinant where you have a kernel on the full line, not just in a circle.
Yeah.
And I was wondering if there is any progress or if you have any idea or how to deduce this type of Fredholm determinant of kernel on the real line, like the one of McCoy, starting from the type of determinant that you are.
There is a similar thing for ARI in Painlevé II. Is that what you're asking?
No, I was what I had in mind, because I don't think for Painlevé II you have the type of McCoy determinant solution, right? But if you think, for example, of the Painlevé III, the D8, right? Yeah. There you have two different Fredholm determinant two Fredholm determinant representation, right? One is similar to what you worked out, right? Yeah. And then you have another one, which is the Fredholm determinant of an integral kernel. Yeah. Which is the one that I think a long time ago McCoy and other people worked out. And my question is about the connection between these two solutions.
Okay, so there is a similar solution also for Painlevé II with the ARI kernel. So the McCoy is a signed kernel, right?
I see. Yeah. So this kernel is not. It's not of trace class, for example, right?
It is.
Ah, okay.
It is a trace class kernel.
Yeah, this is because I missed the first part of your talk.
So instead of area, I think you get. So for Painlevé III, what you have is something like sine x minus y, something like this.
No, it's not this one.
No.
No, maybe we can discuss later. Yes. Thank you.
Thank you. Other comments or questions? No? Then let's thank Harini again for a very nice talk. And I think, Chris, we can still be on schedule. Let's resume at 11:20. Is that okay? Yeah, we keep the schedule. Okay.
I survived. Was it okay? Oh, so sorry.